Yeah, we have 1 minute more, so can use this for the introduction. So Daniel Black from the MariaDB Foundation, he's a common visitor at our conferences, so we are very happy to have him here. And he will speak about vector search. I just asked him, well, it's one of the main components nowadays a database has to provide, because otherwise, like all the AI guys get crazy without vector search and something we cannot do anything. So let's welcome the speaker, and I look forward to a very interesting talk.
Thank you, Norbert. Yeah, hi, I'm Daniel Black. I'm from the MariaDB Foundation. As mentioned, I'm talking about vector search database. So MariaDB in their 11.7 release in 6 months ago actually came out with our first iteration of a vector search database. So this is now GA at 11.7, and 11.8 has some minor improvements on that, but we'll get to the roadmap of what's to come next and see how long this project starts. But hey, the side ones appear to be working if they fail. So vector search, as is probably already covered, is the technology behind semantic search and image search and RAGs and music search underneath, as you probably know. And so what happens in a vector search database is information in the form of an image, a text, a document is transformed using a content embedding into a vector. The vector is stored in the database, and to search it, we actually put input data from the user through the same embedding transformation, and we get an input vector out. And after that, it's a responsibility of the database to just search for which vector is closest to another vector in the database. So the database itself doesn't actually know about the model at all. There are trickier problems as well. So a vector is just a list of numbers. Depending on the model, it's got between tens to thousands currently in the length of the vector, and it's the model that will actually determine this. So the embedding, the critical aspect of models, as you know, is that similar things will become in a close to each other in a vector sense, and then after it's the embedding's not done in the database, and it's the job of the database to actually find the closest one. Now, the absolute closest object to another, a vector to another vector in a database is a really hard problem. It would actually involve a full table scan and to actually work out the distances. So what we get with vector search is an approximation, which is a novel concept for a database that's sort of typically always precise answers. However, that's a problem space, and that's what we implemented. MariaDB does a fairly common thing and does hierarchical navigable small worlds. We did do a minor modification to the algorithm that we found out gets around like some local minimum problems, i.e., you start searching an area and it's like it's a minimum, but it's not a minimum over a big area, and we've got some on the models we've tried some good outcomes of it. The algorithm's a in-memory algorithm, so once it goes beyond memory size, it performs horribly, and that's just the nature of the algorithm. It needs everything in memory. As usual, this model is a optimum trade-off between speed and precision, which is what people want their answers quickly, and they want a reasonable level of precision, and they're willing to sacrifice a little bit on both, and how much depends on the application. In an SQL sense, thanks for the SQL introduction before, that what tends to happen is we get a embedding as a vector type. The vector's got a length in a typical SQL way, and that's the number of elements in the vector, and there's an index on the vector. So this is all pretty standard as far as the SQL goes. If we're using something like OpenAI, what we do is we actually use the Python libraries there just to import it. We do an API call out, and we get an embedding vector back. And that's all it is as far as the Python goes. When we do a search, we do the same thing in reverse. We get the input vector, we get the embedding. The embedding's a set of numbers. This is inserting. So inserting into the database, and we've got a vector from text function that does all the conversions. So all pretty standard SQL on that. The search, we take a user input through the same embedding algorithm, and we do a select from the table, and we order by the vector distance between what the user sort of passed in that vector to what the embedding column on the table was, and do a limit. And this is how we get like the 5 closest vectors in pretty much the same way as any SQL query has been since COD invented it. If we're using a framework like Llama Index, there is a MariaDB Vector option. We pass a set of database parameters, which are pretty standard, and then we've got a hint that sort of says the vector column is such and such, and it's a type and the length of it, and thereafter you pretty much use it the same as a vector store in Llama, if you're familiar with that sort of thing, which honestly I'm not, but hopefully someone is. That's why they invented them. LangChain, similar thing. We import the Python module, we create a vector store, pass a series of parameters. There is a vector distance strategy as a cosine or Euclidean in a typical way. The embeddings are part of the arguments, and same with the length. There is whatever models you use in OpenAI. For tuning, what MariaDB went for is, if you look at like the hierarchical neighbors small worlds algorithm, there is a bunch of tuning parameters there. So what we've done is we've minimized them down, i.e. this is the entire list of the tuning parameters available in MariaDB on that. And we've done this so it's nice and easy for the users to get a grasp of, and sort of hides the complexity. At the basic level, there is a distance algorithm with Euclidean or cosine. You'll know when you're using the model as to which one should be actually being used. We've got an M value. It's got a hard limit of 3 at the low and 200 at the high. But realistically, as we'll see in the benchmarks later, 8 is about a good value. If we go up to 32, that's probably about the realistic maximum, but it can depend a little bit on the algorithm. What's important to note actually about these is the M value is what PG Vector and other algorithms might actually use as an M value, and the EF search below isn't actually always portable across it. So if you switch databases for some reason, don't assume what was there used before is exactly the same on the new implementation. EF search is like the number of search items into the index that we're actually going to do to get the results, and we'll see the impact of that a bit later. As mentioned, it's an in-memory database, therefore it's got a size. If you go beyond that size, it starts swapping, that's bad, and it slows down significantly. So there is a cache size parameter, stay within it and you'll be all right. So F and M, so we have a choice in vector searches to we do slow and precise or fast and imprecise. And the other trade-off we have is when you're actually building an index, you can build it really fast and have a slow search, or we can build it slowly and get a faster search. And that's just the nature of the algorithm trade-offs. As far as the parameters go, the EF search only affects the search as far as to how deep we go, and the default M actually affects the search on the right. So with these two parameters, we've got a good control over the trade-offs between precision, speed, and also the consequent building speed associated with that. As before, I mentioned that the M and the EF search values are actually different from PG Vector or others, and what typically happens if you're using MariaDB, that you'll be using a lower value of M than PG Vector. The benchmark I'm quoting from is Mark Callahan's benchmark. He's been doing benchmarks for years, and there was a bunch of hardware at HNSW that you can read just as well as me on that. So this was an ANN benchmark that was done for no particular, there was probably a reason, but it was a common one that there was a lot of implementations from PG Vector, from Quadrant that I'll mention, that have actually contributed not only the tuning parameters, but the mechanism to actually run the tests, and that's what he did. Noting a few things from actually the full slide, I'm just going to abbreviate on these. MariaDB uses 16-bit integers rather than a full float 32 to actually do the search. PG Vector uses a float 32, though it's got a half vector option that is a float 16. Now, float 16 still has got about 8 to 10% bits of precision, and MariaDB's got a little bit more, so we're getting a good result by moving away from the floats. Quadrant used like a 32-bit int, but they've also got like an 8-bit scalar, and I'm not too familiar about their implementation, but it'll, you'll see the results of that on the benchmark. So we've got a graph of like the three of these on the bench. MariaDB, PG Vector at half vec, PG Vector at full vec, and the quadrant implementations there. So we've got the scale on the vertical axis is like queries per second. Obviously, the more queries per second, the better. The less resources it's actually using. At the bottom, we've got the recall from a perfect match over here to a less perfect match over here at like 0.7%. Everything I've heard is like anything less than 95%, don't really worry about, so probably ignore this half of the graph. But, you know, it shows the trends. The points here are the optimum EF and the M value for various points, and I'll go through a couple of results of that now. So if we look at like a perfect recall as well, what happens is what MariaDB gets down to a 18.3 queries per second, and we'll look at like some of the search parameters for that. We've got like an M value of 32 and an EF search of 200. If you look at like PG Vector is what they took to actually get the same thing, it was an M value of 64 and an EF search of 400. And this is, I guess, showing that across implementations, different values are needed to get the same results. So sure, we're actually quite admittedly slower on than PG Vector to get that 100% mark. However, I guess the hierarchical navigable small worlds problem is about getting an approximate result quickly. So this isn't actually the case we optimized for. The case we optimized for is closer to this one. It's like, give me 99% results and make them quick. For this, we got an M value of 24 and an EF search value of 10. And if we look what it was before, the EF search was 200 and M value was like 32. So we've dropped it down significantly by just that precision going down. Mark measured the PG Vector results in the PG half vector, and they're half to 43% as per terms of queries per second compared to what MariaDB does. Quadrant did a little bit better, 66 to 98, 89, sometimes dyslexic, percent to get of the queries per second. I'm not going to go through too many of these. If we go down to 98%, a bit more, our M value from MariaDB before was 24, and now it's down to 16, but we've had like a 50% increase in the queries per second by just allowing that little 1% margin there. As we see, the PG vector is around 40% of that, and quadrants drop down a bit. Last one, I promise on the thing, if we drop the M value from 16 down to 10, we get a recall above 95%. And the queries per second went up again by, what was it? 1,200 to 1,600 queries per second. Oops, on that. So, yep, that's all I'm going to look at tables. So last I'm going to cover where it's actually supported. I showed the Llama index before. It's in that, it's in OpenAI, it's in the Hibernate. There was a LangChain discussion, however, it ended up that we'll do our own module, and that's been published now. LangChain 4J is out in the 1.0.0 beta 1, and there is a pull request in the LangChain JavaScript as to what an implementation there. So where to from now? Well, in some ways that actually depends a lot on where the users actually want to take us. There are different distance algorithms, there is Manhattan search and that kind of thing. If someone's got a good use case around those, there are tickets in MariaDB's thing to describe that, and we'll implement whichever's got the best business case around it. As mentioned, this is like hierarchical navigable small worlds. So there are other implementations like Ivy Flat. There's like DiskANN as that. So Ivy Flat is a faster algorithm with less precision. DiskANN is one that actually gets us beyond an in-memory database to something that tolerates a few things that won't fit in memory at the same time. So there's those kind of trade-offs in place, and those are both on the possibilities of things that we can implement. That's pretty much all I had. So is there any questions?
Well, first, let's thank the speaker. We have ample time for questions.
Okay, so all perfectly understandable. Okay, questions, Yeah.
So in terms of sort of memory requirements, is what you showed for the benchmark a sort of typical what you would expect, or what's the minimum it can go down to in terms of memory?
Terms of like memory?
RAM, yeah.
Yeah, it very much depends on which model is happening and how many elements in that vector of that model. So if you could have these are, I think they were like 1536 OpenAI kind of length vectors. If you went for a model that sort of generated 10, 100 things, that's, I guess, 10 times less on that. You've got a tricky question for me, don't you, Alkin?
Tricky question. Okay, you can have this one.
Okay.
So, okay, the follow-up on the memory question.
Yeah.
So this is, you create the index and it's in memory. Do you keep that, a copy of that in the disk, external disk?
Yeah, it's all persistent. So it's got our usual storage engines underneath. It's supported under InnoDB and ARIA and MyISOM underneath. they're actually worked out to be kind of hidden tables underneath. And I think if you're familiar with the algorithm, it's a bunch of graph-related things that are stored to implement the hierarchical navigable small worlds. So it's those hidden kind of tables in the same way.
That answers my question. Thank you very much.
Excellent.
I have more questions, but let others ask. We have time. The other question I have is when the benchmarking is done. I know it's Mark did it, but do you have some sort of a idea of memory consumption during the benchmark versus
During the benchmark? I don't think Mark actually published that.
He didn't.
No,
actually. Maybe you had some insights into it.
No, sorry, I don't have any more info on that.
Okay. So, all right, that's enough. Thank you very much.
Thanks a lot. Any further questions, comments? Wish list items?
Yep. If not, you know, my LinkedIn profile is actually up on the page, and you feel free to message me there or daniel@mariadb.org. But, you know, most interested actually, you know, where to go next. You know, should we be doing an IB flat? Should we be doing, you know, Manhattan distance function? Should be anything else? Oh, the other thing that was coming if you do a vector search and say you want to apply a where criteria of like where, you know, region equals X, we've actually implemented so that, and what typically happens, you want an order by a limit. MariaDB works in the way you expect for SQL. So if you set a limit of like 10 or 100 results coming out, it will give you 10 or 100 results, even if you apply where criteria to that, and that's pushed down into the engine. It's something we're going to work on making a little bit faster too, but at the moment it performs pretty much the same as without a where clause, but, you know, filters it appropriately.
Okay, then let's thank the speaker again.
Thank you.